Testing. Testing. Okay. Okay, good afternoon everyone. All can hear? Can you hear me? Hi. Yes, good. Maybe I will start the lecture in 5 minutes. So today I will finish the analysis of algorithm. We have this Monday we already introduced you what is the big O notation or the asymptotic notation, the big O notation, big omega, big theta, and how the definition. So these are the definition. There's no any theory here. It's just someone define it in this way to represent the function in big O notation, in big omega, in big theta. It's trying to represent the order of growth. Okay, order of growth of the time complexity of an algorithm. Okay, so this is the thing we cover on Monday lecture. So today I still have a few slides to summarize this thing, and then after that another important is the assignment. I will introduce just one. I think probably take half an hour, should be able to finish this advanced data structure. It's nothing complicated, although called advanced. It's just one application. I just want to share the algebra expression, how the computer calculate the algebra expression by using the transform and conquer. In maybe half an hour, I guess. Should be able to finish it. Then all this is in the notes, right? Yes, it's in the notes. See whether I can retrieve the notes. Do I have the notes? My lecture notes. Lecture notes. My lecture notes. Upload. You should be able to, in fact, everything, the first lecture or the introduction, already mentioned here, whatever I want to say. Sometimes if I miss out anything, you still can refer. I cannot regenerate all the material exactly. And then if you find that not enough, you want to know more, there are this is the textbook. I have, it's not with me. This textbook is very classic, the comment algorithm. Nearly every faculty should have one algo. In computer science have these textbooks. It introduce all the algorithm, all the basics, conventional, standard, typical algorithm is inside this 600-700 pages textbooks. This is one. Another one. The rest are also not too bad. You can try to read them. This one also is a good textbook, Introduction to the Design and Analysis of Algorithm. Okay, so these are the things you can try to, the textbook, you can get more information if you want to learn. Of course, this is the introduction modules. So we not actually, this one got 30 plus page chapter. We only introduce 2-3 algorithm from the textbook only. So actually a lot of things about algorithm we don't really cover. We don't have time to cover everything. So if you want to really learn it, you probably have to refer the textbook. Then algorithm, analysis is in the slide. Actually all the things you find that what I mentioned, more details, the definition, the example, all this is here. I just select certain things and highlight. So lecture, I trying to make it more like Q&A. So if you have any question, I try to answer it. But of course we have the times. I only have 1 hour. So That's why I still encourage you all to attend the live lecture, because you watch the record, maybe not much help. Basically, yeah, it's same as you just go and read this one. Yeah, you want to, I think this one can read for you, right? Yeah, can have a, yeah, they can print out, they can read, activate, then basically just read out the notes. Yeah, I think no point to generate this kind of video for you to watch. Yeah, so that's why I provide all the things I want to set. If anything I miss out, yeah, the material basically, yeah, is here. Yeah, all the information you need to know, yeah, it's already inside. I already trying to summarize everything I want to set in these notes. Yeah, you can refer to. Again, all this lecture is the concept. Yeah, you understand the concept is still not enough. You need to be able to implement, realize the code. Yeah, that is another learning outcome you need to have. Yeah, but blindly know how to implement also may not enough, because you need to understand the concept, because next level will teach you more advanced. Why you need to learn all this analysis? Yeah, because when you have more complicated algorithm, yeah, you need to decide which one is better, and before you implement them, yeah, or you need to sort out the algorithm, what is design the algorithm, you need to consider the complexity. So yeah, it's not simply implement just good enough. Yeah, as the next level, higher level, you should expect that you need to be able to do some analysis. So the theory and the application, the practical, both are equally important in computer science, computer engineering program. Okay, so let us start the lecture. So that day, I think we stop at here. Maybe I already introduced. Okay, one thing, yeah, I think I make a typo, should be 3. So this thing, there are 2 ways to find out the big O note. Yeah, the definition, there are 2 definitions of the big O notation, big omega and big theta. One conventional definition is trying to, big O is let the f and g be the 2 function, and then f is the time complexity. So we said that fn is in OGN. That means f is bounded above by some constant multiple of gn for all large n. That means after the n-naught onward, the fn is always bounded above by this particular CGN function. Okay, so then we can conclude that fn is in OGN. So as long as I can find the C and n-naught, fulfill this criteria, then I can make the conclusion saying that fn is in OGN. In computer science, they just simply write equal to OGN. Yeah. So this thing I've been covered Monday. So one typo I make mistake is here. So another approach is using the limit. So I can let same thing. You have 2 function f and g as a 2 function. So you can try to take the limit. The reason you can take limit, the reason is very simple, because if fn is grow slower than gn or same rate, definitely this limit, this ratio, you take the limit and go to infinity, it definitely less than infinity. Yeah, if you understand this thing, the idea behind, then you can actually using this alternative definition to determine whether fn is in OGN or not. Yeah, so example I give here, I already correct the typo. Yeah, it should be 4n plus 3. fn is 4n plus 3 over gn is n. So you take the limit. So that's surprising. You're equal to 4. Okay, I hope you know how to find the limit. If not, you can refer the max revision, the lecture 0 notes. Yeah, inside I have mentioned how to find it briefly. If still cannot find it, you probably have to go back to your, I think this one should be in your O level. Yeah, notes or textbook. Yeah, That's why we don't cover all these things. You're supposed to learn this stuff in your O level or or your A level or your poly times. Yeah. So this thing, if it's less than the infinity, so I also can easily conclude that Fn is equal to OGN. Yeah, because both are linear function. Actually, you also can easily find out both these two functions are linear function. So the limit is constant, definitely less than infinity. Yeah, another one is the 4n. One is the linear, the other one is the cubic function. So not surprising, 4n plus 3 over n power to 3. So this one will grow faster. So you take the limit, you will find that this thing is equal to 0. So if it's equal to 0, less than infinity, again, based on the definition, less than infinity, you can make the conclusion saying that Fn is equal to OGN. Okay, so similarly to the big omega, it's just the other way. Instead of it's bounded above, now it's in the big omega notation, the definition Fn is bounded below by some constant multiple of Gn. So this thing has been covered in the Monday lecture. So another one is the big theta. Big theta is bounded both above and below. So it's a tightest bound. Yeah, you must fulfill two criteria. So if the function Fn, we said Fn is in big theta Gn, that means that Fn also is in OGN, is also in big omega Gn, because you need to fulfill two criteria. The above is bounded above and is bounded below by some constant multiply of Gn. Yeah, so that is these three notation you need to know. So that's why we said that Fn is big theta Gn. That means we said Gn is asymptotic type bound of Fn. Yeah. Okay. So summarize. Yeah, you can try to take the limit. Okay. I don't know why. Let me. So if you're trying to take the limit, let's say n go to infinity. Yeah. So Fn over Gn. If this limit, is equal to 0, implied that, Fn is in OGN. If this limit give you is a constant, implied that it's a tighted bound. Tighted bounds mean that it's big theta Gn. It also, once it is a big theta Gn, that means this thing also is a big omega Gn, also big OGN. Yeah, definitely is bounded both above and below. Yeah, then if the limit give you is infinity, then it is Fn is in big omega Gn. So could you explain a bit more? n-naught is nothing. n-naught is just any number. As long as you give me a function, you can find a number n-naught, any number. This number can be anything. As long as after this number onward, for example, in this big omega notation, your Fn is always above. So it's bounded below by some constant Cgn. Then, you can conclude that Fn is in big omega Gn. So it's just a number. As long as you can find a number. And then, any number greater than n-naught. Any number greater than n-naught fulfill this criteria, then you can make the conclusion. Because as I said, that all these things we're talking about order of growth, we only concerned about when my n getting bigger and bigger and bigger. How does this algorithm, the time complexity affect? So of course, people interest is about you have a bigger and bigger and bigger input. How does your algorithm affect? So that are the things we interest to know. So people trying to use this notation, big omega, big O, or big theta, to represent this time complexity, to give people an idea how complex, how difficult, how good, how bad it is about this algorithm, the time based on the time complexity. So we want to bound the entire function. So this function, if let's say Fn is a time complexity, that means this function, no matter how your n it is definitely always above this Cgn. definitely greater than CGN. Yeah, that means CGN definitely is less than FN. The question will ask like, what is the time complexity for above the TN, for example? What is the time complexity for above the TN, for example? I don't get your question. So the question asks us the time complexity of 4n. We can put, okay, 一号 question. Okay, I trying to, okay, next one, let me later answer the 一号 question. Okay, this one already share with you. So why I keep saying that computer science people will say that although Fn is in OGN, yeah, this is by right because it's a set of function. Okay, so but in computer science normally they write it in Fn is equal to OGN for convention, but actually mathematically speaking, this notation not very correct lah, but normally they do so. So because the reason is like when you analyze the algorithm, a lot of time, yeah, you can rewrite it in this way. Like if you have some time complexity, you do some calculation, you got 2n squared plus 3n plus 1. Yeah, then you got this. You can write it is like, yeah, this part is a linear. Yeah, you can write it in this way. Or sometimes you have some recursive function, you may be right in this way. So you only know that each recursive function call, is you need to do some big theta n and so on and so forth. Yeah. So yeah, the question is like all these things. Yeah. So I can have some function like just now he mentioned 4n plus 3. Yeah. So this thing, yeah, if you have a function, maybe I use a function first. Yeah, if you have some function, it's a 4n plus 3. Of course, you can set this 4n plus 3 is equal to OGN, or n. Yes, nothing wrong. You also can set this thing is O n squared. Well, it's not wrong. Okay, that become a problem is like, you're talking about for the test or for the exam. Yes, technically depend the question how I ask you. Yeah, if I ask you is what is the most appropriate representation in big O notation about this time complexity, of course you should try to represent it as theta bound as possible. Because of course this thing is nothing wrong. You even can say that this thing is 2 power to n, also fine. You also can set this thing is whatever n squared plus 2. Yeah, it's also correct because they also based on the definition. You look at the definition, yeah, they all fulfill this criteria. But what is the most appropriate answer? Yeah, so you actually should trying to, normally we write this notation is trying to represent the order of growth. We're trying to tell the reader the best representation about the order of growth. Among these, based on the definition, is not wrong, but this should be the best one. And if we can represent in theta bounds, normally the most appropriate one, I can represent it in theta bounds. Of course, I should do in theta bounds. Yeah, I should not trying to represent in big O or big omega. Yeah, technically correct, but not the most appropriate answer. Okay, so there are so this big O notation, big theta, big O, big theta, big omega. Yes, there's it can be right in any just like any algorithm. Yeah, I don't need to look at the algorithm. It is. I just said that it's definitely big omega 1. Yeah, also can. Yeah, you can find anything worse than that, man. Yeah. So that become meaningless. You write your time in practical point of view or for exam point of view, you write this kind answer is pointless. People still have no idea about this algorithm. it doesn't represent about its time complexity. Yeah. Same thing, yes. Another person said, yeah, most likely you can't find anything, yeah, worse than this. In fact, there is if you have an algorithm, it's like n power to n. Yeah. So this kind of representation is meaningless, and that is not the right way to represent the time complexity. Yeah. Based on definition, yeah, you can claim that this notation is correct. Yeah. But the answer, yeah, likely we will say the most appropriate answer. Yeah, that is not the most appropriate. Definitely got other better way. Or sometimes I may ask is like, I want you to represent in tighter smile. Yeah, definitely this one you cannot do so. Yeah. So the third line is a bit yeah, sorry, there's another type. Yeah, this one should be big theta square. So all these things you can trying to write in many form, and you can trying to use this or big theta, normally big theta to help you to represent the time complexity and simplify your time complexity representation. As I said that we only want to represent the order of, people only concerned about the order of growth. Yeah, you want to express this thing in the asymptotic notation is trying to show them the order of growth. Yeah. Later you will see in the graph, yeah, you may see more. I think here all are just using one factor input. Later in the graph, you will see all this complexity we will represent not only one factor. We also need to consider the number of vertex and number of edge. Yeah, then thing may be a little bit more complicated. Sometimes you may have one is about the edge, one is about the vertex. Yeah, sometimes you also maybe can represent your complexity in this way. Yeah, you will see it in the graph. Yeah, but here normally we only consider one factor. Okay, so you also can do a lot of simplification. So if fn is equal to all cgn, so for any constant, yeah, of course you can write, since that means this thing means that if I have a 4n, of course this thing is in O 4n. If I can set so, then of course I can set this thing is equal to ON. Ideally, yeah, same thing. That means I also can set this thing is in O phi n plus 2. It's correct based on the definition. Yeah, I definitely can, based on the definition, I definitely can find some constant C and some n-naught. After that, yeah, this phi n, yeah, plus C is always bounded above 4n, then I can conclude that fn is in O phi n plus 2. Yeah, but ideally, we just need to know this is a linear function in practice. Yeah. So this is one way. Another one is fn is in OGN. Gn, if fn is in OGN, gn is in OHN. Of course, you can set fn is in OHN. That means if this thing is equal to this, definitely, and n is definitely in O n square. Then that means this thing again, you can conclude that is in the 4n is also in O n square lah. Yeah. So another one, if your f1n is equal to OG1n, f2n is equal to OG2n, then f1, so your first part of your algorithm and second part of your algorithm, you sum it up, what is the total? You consider the worst case, the worst part. That means if it's the first part trying to run a single for loop, so f1 is n, then it's in OGN, ON, then f2 is n square, is n square. So it's O n square. So f1 plus f2, of course f1 plus f2, just now previously you also see n plus n square should be in the maximum O n square. Next operation. So can I set that a function fn is faster than OGN, slower than? Depend your fn. Normally we only set the time complexity is in OGN. How do you set it's the faster or slower OGN? Because OGN is the set of function, it's trying to tell you whether this function is in this category or not in this category. It's not trying to set faster or slower. It is a bit weird. Faster is faster in what sense? Another concept. Okay, let me finish. I think that in the next slide. Okay, let me show another thing. Erase first. So f1n equal to OGN. Yeah. Then f2, that's when you have a outer loop and inner loop. Yeah. Outer one give you is this. Inner one is give you this. So if you combine two of them, of course, outer times the inner one, then it's a multiplication. Yeah. So that's another way to simplify your asymptotic notation. Yeah. Yes. That's why in here, all this in computer science, yeah, they're trying to use the equal signs. You can find that actually they no longer use the in, use this notation. Yeah, they think that thing that is the conventional representation. Of course, I know that all is represent a set of function. Yeah, but here they trying to, because they need to do all this simplification, all this arithmetic algebra stuff. So they a lot of time they just simply use the equal signs to easier for them to simplify the equation. Yeah, the expression. But mathematically, this is not very correct. But in computer science area, all this algorithm, you find that all the textbook, they simply write this way. Yeah, that's why I highlight to you at the beginning. So f1n equal to 3n square, then equal, that's why they said it's in O n square. Yeah, log, then that's why you can combine. So it's a n square log 2n. So one thing, I think just now someone asking constant times. Yeah, the speed is the thing. The just now talking about someone asking about the faster also. So if you have a one function, one algorithm, its time complexity is in O(n). Another algorithm, the time complexity is O(n) square. Yeah. The question is, I think there's the question he asked got two mistakes. One is faster or slower. Which one is faster or which one is slower? This statement itself already have some problem. When you find that you have a big O doesn't really well represent the algorithm exactly. If I said, let's say I said big theta, maybe it's a little bit better. Tightened bound for sure that this time complexity is in linear. This one time complexity is in quadratic. Which one faster? That is second problem. Second problem, what do I mean? If you have a function is linear, that means the problem size n grow, the time complexity grow linearly. The time complexity grow linearly. And then this one is a quadratic. It grow, the time complexity grow quadratically. But when you set faster or slower, you will find that actually this one will take longer times to run. Actually, the algorithm itself run execution will take longer times than this one. Yeah, but this one grow faster than this one. Quadratic one, this one definitely grow, the time complexity grow faster. But the program itself, the algorithm itself will take longer times, will run slower. Yeah. So when you set faster or slower, you need to be careful. You are referring the algorithm, the program itself, or the time complexity, the growth, the order of growth. Yeah. So, okay. Other property about all this notation, asymptotic notation, there's a reflexive. That's when Fn is equal to or Fn. Of course, Fn, yeah, definitely you are equal to yourself. N definitely is in OGN. Yeah. N square, of course, is definitely is in omega n square lah. Yeah, and so on and so forth. Yeah. Another one, easier one, transitive means that, yeah, just I already show you, Fn is equal to OGN. Gn is in OHN. Of course, Fn can conclude that also equal to OHN. Yeah, similarly apply to omega and big theta. Yeah. So last one is the symmetric of big theta. Fn is equal to big theta Gn. So Gn, yeah, this one only apply on the big theta one only. Only big theta. Big or not working. Yeah, very easy example. Yeah, if this one is in O n square. N is in O n square, but doesn't mean, but n square not equal to O n. Yeah. I just use one counter example can easily prove that, yeah, the symmetric part is only work on the big theta only. Yeah. Hard to set what is small, what is big. They don't set what. So it's basically it's not talking about asymptotic. It's trying to talking about the growth. So so-called small is like so small and big. Big means that actually your n, yeah, after certain number, when after that, no matter how big it is, your n, yeah, is always fulfill that criteria. Yeah, always is bounded above or bounded below certain function. Yeah, the time complexity is always bounded above after certain n. Yeah, that's so-called big and small. They not really consider the big or small, it's the trend. After certain number onward, the trend, the asymptotic is the trend, your n grow, the function, the time complexity will go in this manner. Yeah. So summarize. So order of growth, a few lah. Here we introduce a few types. It can be constant. It can be logarithmic. Yeah, logarithmic one we will introduce in the next week about the searching in the binary. Actually, you have learned it in when you learn the binary search tree. Actually, that one if you observe carefully, yeah, actually is the logarithmic. Yeah, your searching is a logarithmic. You take the logarithmic. Yeah, if you go back and observe, actually, yeah, if you have a binary search tree, yeah, actually you know that the height is the function of logarithmic function. Yeah, you're searching every time at every level, you only search once, one nodes only at every level. So you only take log n times to search the item. So actually it's a logarithmic function. Constant, yeah, it's very easy. The finding any things, yeah, you just one formula. Earlier I show you if you know the formula of the arithmetic series or geometric series, you just substitute the n. Your n, how big it is, doesn't matter. The computational times is constant. Yeah. So, yeah, you don't have to really know how to draw those diagrams. Yeah, a lot of time you can see that we can just use the analysis to analyze the growth. Yeah. So another one is, next one is a linear. Linear is brute force search or the linear search. Yeah, you will see these two in next week searching. Then the one we not cover is the sorting. Yeah, merge sorts, quick sorts. Yeah, all these sorting are linear ramic. Yeah, it's n log 2n. Then insertion sorts, those run 2 for loop, all this. Yeah, very likely they are quadratic. Then next one, metric inversion. You maybe learn it in linear algebra. Yeah, actually it's a cubic. Yeah, the complexity. Another one go to more complicated, yeah, exponential. That one, Tower of Hanoi is one. I don't know whether you know about it, Tower of Hanoi. Yeah, this is the so-called the Tower of Hanoi. You have 3 plates. Yeah, you're trying to move this 3 plates from here to here. Yeah, that is so-called the Tower of Hanoi. But each time you only can move 1 plate to one of the tower. And yeah, you cannot move the bigger plate on top of the smaller plate. So you have to put this thing here and then move this thing here. Yeah, so something like this. So the number of move you need to do, maybe not correct. Yeah, you need to move from the left to the right tower. Yeah, you use the middle one as a help you. So each time you only can move 1 plate. That one actually the time complexity is exponential. Yeah, later I can show you. The last one is the traveling salesman problem. Basically, you're trying to, you have maybe US got 50 state. Yeah, they got 50 city they need to visit. You need to find the shorter path to visit all the city and go back to the initial state, initial city, the first city. Yeah, to search all this, yeah, is n factorial. So these are the problem, so-called the hard problem in computer science. Yeah, because they are time complexity, they are order of growth, they are the time complexity, or yeah, order of growth of time complexity is in exponential in factorial. Yeah, in short, the computational time is very expensive for this problem. Yeah, people are trying to search a faster one, but no one can find out. Yeah, lower than this. Yeah, so that is so-called the hard problem in computer science. Okay. When the time complexity algorithm A grow faster than algorithm B for the same problem, then we said that A is inferior to B. Okay. So yeah, this one already explained to you, Tower of Hanoi. Yeah, trying to each time you want move 1 plate. Yeah. So you find that this is the Tower of Hanoi algorithm. You can simply Google search, you can find out. It's a very classic Tower algorithm. So if I can quickly show you this thing, actually the time complexity. If I have this thing and then I'm trying to have 2 recursive call, then each time I reduce the plate by 1. So I need to run 2 recursive call n-1. Then let's say I take the action. I move 1 plate, I take 1 action. So in this one, if you try to derive it, you will inside will do another 2 more. -2. 2 plus 2 plus 2. Then you do 1. Then plus 1. Yeah. Then a bit hard. Then this one, you simplify it, is 2 power to 2 W n-2 plus 2 plus 1. So you carry on to the another recursive call. Inside this n-2, you will recursive call another 2 recursive function n-3. Each recursive call you will reduce by 1, then plus 1. Yeah, before that you already do 2 and 1 step. So here will be 2 power to 2. So you observe it, you keep doing this, The base one is when you only, yeah, when n equal to 0 ma. When n equal to 0, you don't need to do anything. So this thing you keep doing n times. Yeah, you will reach the W n minus n. Then you will find that this one will be 2 plus, behind that thing there's a 2n minus 1 plus 2n minus 2 dot 2 power to 2, 2 power to 2, 2 power to 3, 2 power to 2, 2 power to 2, 2 power to 1, 2 power to 0. Yeah. So that is the complexity. Yeah, then not surprising, this one will be equal to 0. Behind, you can see that actually it's a geometric series. You substitute the function, you substitute the formula, or you trying to derive the summation. Yeah, it's 2 power to n minus 1. So the time complexity of this guy actually is 2 power to n. It's an exponential. And normally, what do you learn? Normally, you find that a lot of time, if your algorithm, you're trying to do 2 recursive function call, yeah, very likely this is the result. Yeah, that's why I think in the first lecture I mentioned the Fibonacci number. You also do 2 recursive call. Yeah, then the complexity also is in exponential. Yeah. So this is the things, yeah, you can observe, you can realize that if you have this kind of algorithm, you have to be careful that the time complexity is not cheap. Yeah, it's not something very low. It's can very likely. I think there are two things. One thing is here is the 2 recursive function call. Another thing is the decrement here is decreased by 1. Every time you only reduce by 1 linearly. Yeah, so the problems, each recursive call, your problem size reduce very slow. So causing that plus you have 2 recursive call. That will end up, if you observe how this thing work through this derivation, yeah, you will find that, yeah, why you will end up is exponential, because every time you reduce only by 1. And then you do 2 recursive call every time. Yeah, so you divide, not surprising, in the end, you will end up this kind of scenario, having a exponential function. Yeah, so that is something we through deriving the time complexity and find out that our algorithm having this kind of problem. Yeah, and then you may through this to think whether have any better solution. But unfortunately, this problem is very classic. I think very unlikely you can think a better way to do. Yeah. So the rest, this is the time complexity. So that's why you need to learn the time complexity to analyze the algorithm. Space complexity is similar. Basically, it's just trying to, instead of count the number of primitive operation, you're trying to count the memory usage. So basically, you're trying to look for how many data structure you declare, and you create how many array in the algorithm, and so on and so forth, to determine the space complexity. And later in the searching algorithm, you'll find that, a lot of time we trying to do is there's a so-called space and time trade-off. You want to have a better algorithm in time complexity. A lot of time you're trying to use more memory to store more result information, so that you can use lesser time to solve the problem. Yeah, you improve your time complexity. Sometimes your space complexity will get worse. Sometimes you want to improve the space complexity, then your time complexity will get worse. Yeah, there's so-called this kind of trade-off. Yeah. So, well, that is what we're going to, we just briefly introduce this, how to analyze the algorithm here. Okay. Let me answer one question. Is the +1 due to the constant? Oh, okay. Just now I think it's talking about where's this one +1. Actually, here I just want to count the number of output print. Sorry, this one should be in C++. I forgot to change. Yeah. Anyway, this is in C++ algorithm. Yeah. Yes, I just want to see how many steps I need to take, because it's every time you only trying to move one plate. So the middle one is trying to move one plate. So the +1 is come from I move one plate. I take one. Every recursive call showing that I take one action. I take one action. Okay. So it depends. Space is important or times is important. I would say it's case by case. But in today, normally space computer, if it's normal computer, we have no issue with the space. We just want to let it finish as fast as possible. We can easily get a very large storage today. So normally we focus, that's why we spend so much time about the time complexity instead of space complexity. And then, but in certain circumstances, like you are working on some embedded system, just now I have one. This one, for example, this board is only have 32 kilobyte. I think 64 kilobyte memory or something like that. Yeah, you have very limited memory. Then memory become very important because the device don't have so many memory. Then you have no choice. You have a resource limitation. Then space become somehow quite important in that circumstance. Yeah. Is one recursive call or two recursive call? No, I mean that when you have two recursive call in your function, yeah, I'm not saying guarantee 100%. Very likely that this algorithm, the time complexity will end up is the exponential function. But may not be always true. Yeah, because again, I said that you notice that another factor is like how slow the problem reduce in every recursive call. Yeah. Okay. So yes, for the embedded, in short we call not only microcontroller, it's embedded system. Yeah, you may have a limited memory resource in whatever resource. So sometimes we consider the space, sometimes we consider the times. But generally speaking, especially when we study the algorithm, people study in algorithm, time complexity is still the most critical one. Yeah, because normally today computer, storage in terabyte, in gigabyte, terabyte, it's not an issue. Yeah, but times is an issue. Yeah, like I said, you have an exponential function. Yeah, your computational time is in your computational times, you have a life limitation. You only can wait for 100 years, maybe less than 100 years. Yeah, so your result must come out before that. No? Yeah. Okay. So here, next one I'm going to introduce is the advanced data structure. So basically, here I just introduce one example, which is using the transform and conquer. In fact, before that, I think Dr. Owen already introduced another example using transform and conquer, which is the tree balancing. That one also using, if you learn in linear algebra, I don't know whether you heard about it, the Fourier transform, or in people working in control or something like that, there's a Fourier transform, Laplace transform, all this, it's a kind of a transform. When you, in this particular form, your algorithm is not good or you very difficult to solve the problem, we are trying to transform in another way to make our data in another form. Then we solve the problem. We will find that very easy. Okay, the rest we will introduce in the next few weeks. So here I just trying to introduce this and also show you the application of stack and cube. So one of them is the algebra expression. Okay, I think that one you also, I don't know whether have you talked about this, that your compiler, how they actually, you type this statement, they're able to know that they need to do the computation, how they know that which one they should do first. Compiler, how they build out to do this. Why we introduce this is because I think if you study in 4000 module, there's a compiler technique. They need you to know this first. So that's why I need to cover this. So next time you learn the compiler technique, you know, this is a algebra expression, how they calculate, how the compiler work with in fact, your calculator, your scientific calculator, why they know they need to do the multiplication first. If you just key in the number and operation, so actually that is the problem. If you look at this expression, this is so-called infix expression. That means the operator is in the middle. You have two operand, A plus B times C. How the computer can find out that they need to do this first? What is the algorithm? Yeah, to let it able to do B times C and D times E divided by F. Yeah, so that is the problem. Yeah, how the computer interpret this string, because basically you provide is a string, you key in, user key in the expression. Yeah, computer how they learn. Yeah, they need to know human have this rule that multiplication and division have to have a higher precedence and than the addition and subtraction, and then they need to do from the left to the right. This is the rule, yeah, defined by human being. Yeah, so how the computer can understand it. So yeah, if you find that a lot of time, maybe some people also need to provide some paradox. They know that which one will do first. Otherwise, there's an ambiguous. It can be this way, can be this way. There's a lot of order. You can A plus B first. You also can B times C first. Which one should do first? Yeah. So that is the problem. How do we? If you find that if you directly solve this problem, that means you need to keep searching that where is the multiplication, where is the multiplication, where is the division. Then after that, you need to sort out which one should do first. This one should do first, and then this one should do first. Even you have the paradox, you can see if you read this character followed by this character followed by this character, is it means that you need to do the calculation first? May not. If you here you got two pair open, yeah, this one should do first or later. Yeah, sometimes, yeah, you having the paradox can help you, but I think the computational times, the algorithm still not very easy. Yeah. So yeah, you find that using this infix expression, yeah, the evaluation, it can be done, but it's a bit tedious. Yeah, you need to keep searching, scanning, yeah, to find the next operation in the expression. Yeah, you need to keep multiple scanning. That will become your algorithm become less inefficient. Implementation also very tedious. So how actually we do the calculation? How the calculator actually work? Yeah, imagine that. Okay, I'll tell you how to transform first. I'm trying to show you is like how we do. Computer basically were trying to convert this expression from infix to a postfix expression. That's when the operation will be moved to the operator will move to the back. Yeah, postfix expression. Yeah, if I can, later I will show you how to do this. But first, you see if you do this, after you transform this expression to here, you just need a stack. You can solve the problem. Yeah, because first I read A, I push it into the stack. I read is B, is still operand. When it is an operand, I push it into the stack. Then when I read is C, I still push it into the stack. Yeah. When I read there's an operator multiplication. Yeah. Then I trying to port. When I read 2, then I port it out. I port 2 operand B, C and B out, and then do the multiplication, and then push it back. Yeah. Then the next one will be plus. Yeah. Then again is an operator. You will port these 2 out and then do the multiplication. Indeed, I'm doing exactly just now B times C. Then you see there's a plus. Then you do A plus B times C. A plus B times C. Then you read D, you push it in. You read E is an operand. Then you just push it into the stack. Then when you read an operator, you port 2 operand for you to do the calculation. So the whole process become very systematic. When you read is the operand, you push into the stack. When you read the character is the operator, you port 2 out, and then you do evaluate it. Yeah, then you push it back. You keep repeatedly do this 3 steps. You can solve them. You can find out what is the you can evaluate this expression easily. Yeah, so that is the evaluation. But the question is, I think now the key, the key thing is how to transform from infix to postfix. Then I can apply this. Right? Yeah, if I can transform this, then The evaluation step become very systematic and easy. I just need to read. If it's operand, I push. If it's operator, I put two things out, evaluate it, and then push it back. And then keep repeatedly doing this until the whole expression done. Yeah, that is the calculator, how it works at the back, which you can see. Yeah. So the thing next, okay, now evaluation, no problem. I want to find how to do this thing from here to here. And that is the post, yeah, this thing is known as postfix expression. Basically, you're trying to put two operand in front, then the operator at the back. So after, yeah, so-called post, yeah. So yeah, also known as a reverse Polish notation. In fact, this thing is invented in 1950. Yeah, it's a quite old. Before you have a computer, people start thinking all these algorithm want to make it systematically way to solve the problem. Yeah, before you have the calculator, people start thinking, yeah, all these things. Yeah, so you will find that this way can help you to reduce. You don't have to keep scanning, so that means the memory access will be lesser. Yeah, but the key is how to transform this thing. Yeah, so, but the idea first, you need to know that actually human being how to do. First, we need to do this. Yeah, from the expression, I know that I need to do this. So whenever I check, I need to make sure that these two are do first. So if I do the expression, that means these two intuitive, I make it as a postfix expression. That means I will transform BC to the front, then this thing to the back. DE to the front, this thing at the back. Then next one after that is next calculation is this one. So I need to move this one and this one. These two become a operand. Okay, D times E is one operand. After you multiply, the result is another number. So these two will move to the front, and then this division operation will put to the back. Operator will put at the back. Okay, then similarly, the A plus B times C, will become ABC times plus addition. Okay. Then minus will put to the back. Yeah. So this is what I need to do. But how can we systematically transform the infix expression to postfix expression? Yeah, how to, just now this step is a bit, I think you use some intuitive, you know that you need to do B times C, you know that you need to do D times E, so you do first. Yeah, the thing is how to do this transformation systematically. So this is the matter, this is the algorithm, how actually it works. Basically, there are a few things. You definitely read you given you a string. Yeah, you definitely read from A plus B, you definitely read left to right. Yeah, so every time there are a few scenarios. Okay, not only this, just now those example I'm not including. Here I also further including the paradox. Yeah, he also can handle. This transformation also can handle. So basically I just read character by character. Then whenever a few possible, I can encounter is the operand, can be operator, can be whatever paradox or blanket. So I need to consider what happens if it's an operand, what happens if it's a close or open paradox, what happens if it is a operator. The last one is operator. Yeah, what I supposed to do. You can see, first you read A. You just simply put it at the output or whatever. Yeah, A, if it's an operand, you just put it as output. If you read is a operator, okay, you will run this portion. What will you do? You will check in your stack. You also need a stack. Here also need a stack. Okay. So if at the beginning, not surprising, the stack is empty. So if it's empty, Then I just push the operator in. So the operator will push into the stack. Next one, excuse me, B, you just print it out. Yeah, according to the algorithm. Next one is multiplication. Okay, this time round, my stack is not empty. So my stack is not empty. Basically, what this part trying to do, I need to check whether this plus and multiplication, which one have the higher precedence. Yeah, so that anything I trying to pick the stack if this thing having bigger than the current one, which is the multiplication. This one is not higher, right? Yeah, I need to do the multiplication first. So therefore, if it's not, then you just, if anything bigger than it, basically you will take it out. You will take out all the operator inside the stack which is bigger than multiplication, because they need to do first, right? If it's smaller than this, the precedence is lower than it, then you will still keep it. Yeah, you can see that when I do this step, I use the stack last in first out. So yeah, this one letter will pop out first. That means this one will do this operation will do first. Yeah. So when the C coming in, next I do C. You can see that next step, when I encounter a subtraction minus, I will pop out, because multiplication have higher order. So I pop the multiplication out. When I pop the multiplication out, implied that B, C multiplication will do first. Yeah, then anything equal. So because left to right order, so plus will do first after the minus. So minus will push in. May not be do in the next step. Yeah, so you will push into the stack. Yeah, so basically this step is trying to put out all the higher order or same order, because left to right order, there's a rule left to right. So plus will do first. So I have to put this thing out. Then I will push those operator which is not ready at this moment. So I'll push it in. And next is D. D is the operand, still run the same thing. Then I encounter multiplication again, will push it in, because this one is lower order, lower than the multiplication. Then next I encounter the open. So if I encounter the open one, I still push it in first. Yeah, just isolate the things. Yeah, because this part will do it separately. So E will go in, and then division, then F. Then when I encounter this, this is this part, the closed one here. Yeah, basically this one will keep pop. Will pop all the operator until they encounter this, and then discuss it. Then after that, finish, no more. Then whatever remain in the stack will pop out. Yeah, you're not surprising if you use just now the evaluation. When you scan from left to right, you definitely will do the multiplication, and then you do the plus. Then you D, E, F. So E, F, these two will do the operation. You will do the evaluation first. Then you do the multiplication with the D. Yeah. Then last one is the whole expression with the minus. Yeah. So that is the how we transform from infix to postfix. Yeah, this one is infix expression, the output. Yeah. So the idea is basically this part. Yeah, they're trying to sort out the operator, because whatever do first will be pop out and then push it into the output. Yeah. Then if this thing is the last step, yeah, you will find that during the just now the process, if you look at it carefully, yeah, you find that this thing will stay in the bottom, the stack all the times until the end. Yeah, because it have a lower order, and then the left to right, or yeah, the rule, so you will end up to make this thing, yeah, at the bottom. No, you don't have to really remember, but I think you need to understand the idea behind that people, how they transform the things. Okay. Again, I have mentioned many times, all these things, yeah, you don't have to, it's not really go and remember, it's trying to get the idea people, how the people think, how to transform the things. Yeah, the idea is like you find that you cannot directly solve this problem. You need to find out how, yeah, maybe you can use the transform and conquer to solve the problem. Yeah, this is one of the example. People use the transform and conquer technique to transform into the input into another form, then they solve the problem. Okay. Yes, you need to, yeah, you need to learn is the idea that they sort out the there are two rule, yeah, then yeah, and I need to consider every cases, then different rule, I need how to use the left to right and all the precedence, all this, how to say I won't ask exactly the same question in the exam. Yeah, so you don't expect you go and memorize it, you can survive in the test. Okay, the good news is you don't need to remember. The bad news is like you go and memorize it, you can't survive in your test. Yeah, because I won't ask exactly the same thing again. But the idea is there. You will find that after you transform, yeah, the thing, yeah, you will find that they during the transformation they already have, yeah, trying to sort out the which one should do the operation first. Yeah, you can see that this one will do first. Yeah, then next one, yeah, plus, because the left to right, so no issue, you can do the plus first. And you also can notice that in the infix expression there's a paradox. In the postfix expression there's no paradox. They don't need, because just through the left to right, I just go through it, they will do, yeah, all these things can automatically do, yeah, figure out which one should do first. They already, the information about the paradox is already included in the expression. Yeah, then you read the D, you read the E, you read the F, then after that when you encounter an operator, you port it out. You definitely need two operand to let you execute. Yeah, then you need multiplication, you port another two, you do the execution. Yeah, then you do the evaluation. Then the last one, yeah, exactly, that is how the calculator actually do this algebra expression. Okay, so okay, I think in the lab and the coming assignment, probably tonight I should be able to release it. Yeah, I will ask you to, you notice that here I purposely not show you the code. Yeah, I only give you the expression. Yeah, in the notes also you can't find any code. Yeah, because I want you to realize it. If I give you the algorithm in this way, yeah, will you be able to implement it, realize it? Yeah, that is one thing you need to learn. Another thing you also will learn in the lab and the assignment is, yeah, just now is the postfix expression. Then this one is the prefix expression. That means instead of put the operator at the back, now you put the operator in front. Yeah, actually the algorithm is similar to the postfix. Yeah, it's very similar. Basically, again, it's the same thing. You read character by character. Whenever you encounter, yeah, it's operand, or you encounter is the operator, yeah, what should you do? Yeah, if you observe, I think you want to understand this thing, you're trying to see, first you will B times C will be here. You need to put this thing in the front. Yeah, then D, F, Yeah, this thing will put at the front, and then after that, the multiplication D, yeah, you put at the front. Then this one A plus this, so this one, then the last one. If you observe, compare this one and the previous example, postfix expression transformation, yeah, you find that actually there are some similarity. I think that will be one of your question in your lab. Okay, I let you think about it. Yeah, so that is what today lecture about. Okay, yeah. So I would say that overall algorithm is not just simply know how to write the computer program. Yeah, you need to think when you encounter this problem, how do you solve the problem? Yeah. And if I tell you the postfix expression transformation is this way. Actually, prefix is similar, but will you be able to figure out their similarity? Okay, I think the order should be. I think that's how I do. In the lab, you were trying to implement these two algorithm. The transformation. Should not have so many animation. Okay, I give you this infix expression to the postfix transformation algorithm. Will you be able to realize it? That is the first thing. Okay, I think in the should be in the lab. Yeah. Then this one also, if you have the expression, will you be able to implement to evaluate this postfix expression? Then if you can do this, okay, at least you're able to realize the algorithm. The next thing is, if I tell you that this is the algorithm already. Yeah, now the next level, yeah, you encounter so many animation. Yeah, when you if I give you the postfix expression is given, will you be able to implement the prefix expression? Yeah, find out the prefix expression algorithm and realize it. Okay, so I think that is what the learning outcome I want you to do. It's not go and memorize it. So again, not surprising, you go online, you definitely can search the code, but I would suggest you don't do that, because once you see it, you learn nothing. You will learn nothing. The worst is a lot of online, I can share with you, a lot of online algorithm is not correct. Yeah, I don't know why. I find that it's like one person share the code is not correct, then end up that a few group of people just copy and paste, then turn out just like what you did. Yeah, they all have the wrong answer. The reason why I know it's the wrong answer, very simple. I trying to transform it from the prefix to infix, it doesn't work after the transformation. Yeah, I reverse back, it cannot reverse back. That means this thing is not possible, correct? It's not a correct algorithm. Yeah, so I think to learn this thing is not go and memorize it, or go and I can see during the lab test one, a lot of people trying to, before the test, go and print out all the code and then memorize it. Yeah, you should realize that in the end, you may not be able to, if the question is not same as the one you memorize, yeah, you won't be able to do anything. So that is not really the things you're supposed to learn. What I want you to learn in this part is trying to give you an algorithm. Will you be able to realize it? And then this is the first level. And then next level is like, if you encounter similar things, yeah, the prefix expression should be the similar thing. Will you be able to, based on the given postfix expression algorithm, this transformation, to come out another algorithm similarly? Yeah. Of course, I think first is you need to understand, you yourself need to understand how this thing work first, how the prefix expression work first. And then after you sort out the things, and then you're trying to see, systematically do the things, and then you see whether there's any similarity to the postfix one, and then is it you can reuse it somehow, yeah, or with some little modification here and there. Yeah, this is something you probably need to learn. Yeah, again and again, I'm not asking you to memorize it. Don't expect that. I think the lab, the assignment, I will ask you to do this thing because the algorithm is there. It's a open, yeah, all the assignment lab is open book. You can refer the given algorithm. So I will ask you to do this. But test wise, during the test, you don't expect that you go and memorize all the combination. Here got a few combination. Prefix to postfix. Prefix to postfix, prefix to infix, infix to postfix, infix to, yeah, I think got six combination. Well, I'm not stop you. You want to try to memorize it. Yeah, let's us see how you perform in your lab test. Yeah, I personally, I don't think it will work lah. Yeah, if you memorize all the combination. But basically, after you memorize 6 combination, I think you also lost. Yeah, so don't spend too much time to memorize the algorithm. Try to understand, get the idea, and then try to see, knowing this idea, whether you can realize it or not. I think that is the things you need to learn. Yeah, I think need to practice. I think it's also very hard through the lecture. I tell you how. Yeah, this thing need to really practice it. That's why I trying to through the lab and assignment to let you practice. And again. Don't copy the things in your assignment. I'm able to find out. Okay. Anyway, it's up to you. Okay. I think any question I can answer. I have a question about the OGN. How specifically does the GN need to be? For example, if n is power to... Okay. So just now there's a pack W set OGN. If OGN is equal to n power to 1.5, of course you can set that. Of course it's not wrong to set that. It is n squared. But the question, is this is the most appropriate answer? Yeah, the question is whether this is the most appropriate, or yeah. Theoretical, based on the definition, there's nothing wrong to set so. Just like there's nothing wrong to set that this thing is n power to 3 plus 5. Yeah, also correct. Yeah, based on the definition. Yeah, this statement is correct. Yeah, so a lot of times we given an algorithm, so the principle or something like that, if I can represent it in the big theta, yeah, I will try to represent it in the big theta. And only when I'm not able to tell you that this algorithm in big theta, then I will try to choose the big O or big omega. Because sometimes I only know the worst case, or I only know the best case, but I won't be able to tell you in the general scenario. Yeah, what is the complexity? But I know that the worst things is like this thing cannot go worse than n power to 1.5. Yeah, this is the, yeah, certain algorithm you find that is the thing you can set. Yeah, I think here so far you maybe not encounter a lot of time your algorithm only few line only. Sometimes you really don't know. Yeah, they can have a lot of scenario. Yeah, you only know that the worst case scenario is this is the complexity, and you only can tell people that this is the thing you know. So represent it. Yeah, maybe using a big O notation is most appropriate. Yeah, that is the best you can do. Yeah, then okay. Yeah, but then back to another thing, since you said so. Yeah, if this thing is 1.5, can you set that? Are they the same? Is it okay to say so? Okay, before I end today's lecture, again, I just use the limit Fn over Gn. No. You take the limit. n go to infinity. This thing limit n go to infinity. What is this? Will be n. N will be, this thing will be 0.5 ma. Negative 0.5. Yeah, n go to infinity. That means this thing should be go to 0. Then, actually, it's not constant. It's not non-zero constant. Yeah, it's not a positive constant number. So, that means you cannot say so. For big theta. Yeah, that's again show you that why using big, if you can represent the time complexity in big theta, we should try to represent it in the big theta. That is most appropriate representation notation. Yeah, if you can, like I said, if you can find the tightest bound, why not? Yeah, only when you cannot find the tightest bound, then you have no choice. Then you have to choose the big O or big omega. So that is how to judge. But of course, again, share with you, I think normally you online, you search all the algorithm here and there. People, just simply use big O notation. It's commonly in use. Yeah, because a lot of time I think it's a convention. People just lazy to think so much and just simply say big O n square. Yeah, safe. Yeah, because big theta, you need to be careful. Very careful. It's tightest bound. Yeah. Another question for multiple recursive call. Do we need to consider the space complexity on the call stack? Okay, when we talk about time complexity, is time complexity. When you talk about space complexity, yes, recursive call involve the space complexity in their stack memory. Although you didn't physically see it in your algorithm, you didn't declare a stack in your algorithm, but actually each recursive call, you actually indirectly create a stack memory. You push your current call into the stack memory, so later you can recover back when you return from the call, from the call function. Yeah. When you return back, so actually that involve memory. That is also implied why sometimes you do the recursive call endlessly, then your program crash. Yeah, when you run out of memory. Yeah, it involves the space somehow, implicitly. Although your code, your program, you didn't write it explicitly right now the stack memory, where create a stack, but implicitly when the program, when you run, when you execute, actually at the back you really use it. So that should be considered when you consider the space complexity. Okay? Any further question? If not, I will end. Again and again, if you have any question, you still can send an email to me to seeking for consultation. But don't wait until last minute. Like I said, that last minute, memorize the code, read all this. Just start learning. Usually for this type of module, need to practice. Need to train your computational thinking, algorithmic thinking. It's not overnight stuff. Some module can. You just read through all the notes, read through all the past year paper. Maybe you can survive in certain module, but probably not in this programming or mathematics module. Last minute just start learning. A lot of time is you just realize that it's too late. Well, okay. If no further question, I will stop today's lecture. Goodbye.